In this video, we are going to discuss about the modern block ciphers because uh, the traditional ciphers are character oriented, but we know that with the advent of the digital computer, we need it to be the bit oriented cipher. And why it is so? Because it is not only the text which has to be kept secret. Besides the text, we have to make the encryption, the decryption process of many others, such as numbers. We have to make graphics, we take the audio, video, all these kinds of the data has to be encrypted. So whenever we have to work with all these kinds of the data, it is convenient for all of us to convert these informations into the bit of stream in the stream of bits, so that it can be easily encrypted or decrypted. So that is why we are working with the modern block ciphers. So what is modern block cipher? Now in the modern block ciphers, uh, the encryption and the decryption is being done in the form of a n-bit block. And for doing the encryption, we are in requirement, the encryption or decryption, we are in requirement of two kinds of things. One is the algorithm and another is the bit key. So what we do, we apply the encryption algorithm with the help of k-bit key on the m-bit plain text, so that we are able to get m-bit ciphertext. So this is what we are doing in the center side. And in the reverse case, when the ciphertext is moving through the communication channel to the receiving end, the receiver used to receive this m-bit ciphertext, which is being decrypted by decryption algorithm using the k-bit key, so that it is able to get the m-bit plain text. So of course, the encryption process and the decryption process are counterpart of each other, and both the processes uses a secret key that is of k-bit. But of course, whenever we are having plain text of m-bit and we are encrypting with the k-bit key, we are getting a ciphertext all that is of m-bit. It means the plain text and the ciphertext is of the same size. So now it may be the problem that if we want to do m-bit plain text encryption, and suppose the plain text which is available is not is less than m-bit. So what we will do, we will add certain padding bits so that it will become the m-bit plain text, so that it can be converted into m-bit ciphertext. It may be possible that the plain text bits which are available are more than m bits. So what we do, we we convert the plain text into blocks of m bit, and each blocks will be encrypted or decrypted at a time with the help of k bit key. So this is about the modern block ciphers. Now, uh, since both the encryption and decryption process uses the same secret key. Now, whatever way the modern block ciphers are being designed, it is designed to act as a substitution or transposition cipher. But in most of the cases, substitution ciphers are preferred. So let us discuss this particular with an example. Why substitution ciphers are preferred and why not transposition ciphers are uh, not preferred. In case of substitution cipher, suppose we have a 64-bit plain text, and since I have already told that modern block cipher uses binary digits in the form of a plain text, and we will be receiving ciphertext also in the form of a binary digits. So what happens, suppose in a particular block of plain text, suppose there are the plain text is of the size of 64-bit, and out of that 64-bit, suppose we have 12 zeros and 52 ones. So once we are doing the substitution process, it may be possible that we will be having 34 zeros in the form of in the ciphertext, and 30 ones in the ciphertext. If the plain text is having 12 zeros and 52 ones, and when it is being encrypted to get the ciphertext, by using the substitution process, it may be possible that we will have 34 zeros and 30 ones. But in case of transposition, if we are applying transposition cipher, and suppose we are having 64-bit as a plain text, and suppose we have 30 zeros and 34 ones. So what we'll do in the case of transposition, only the bits positions are going to change, but the number of zeros and the number of ones remains already same. So it gives the some intuition that if we are adopting only transposition process, then the vulnerability of the ciphertext become more. So what we do, we used to use, we designed in such a fashion that we will be acting on the substitution cipher, because substitution cipher will be preferred, because the attacker is not able to conclude any kind of idea, because the input may be having 12 zeros and the output may be having 34 zeros. But in the case of transposition, whatever number of zeros and ones are available in the plain text, the same number of ones and the zeros will be available on the ciphertext. So that is vulnerable. So that is why substitution is preferred than the transposition. So, but in practical, we not only use substitution process, but we also use the transposition process, and that is why the modern block ciphers, whenever we apply an algorithm to convert in plain text into ciphertext or ciphertext into plain text, we have to use many components, and these components are the combinations of these components makes it more tougher for the attacker to work on that. So modern block cipher is made of combination of the transposition, that is also called as P-box or the permutation box, and it is also consists of substitution units, that is the Sbox, as well as besides P-box and the Sbox, that is the permutation box as well as the substitution box, we used to use the some other components also. So we are now with this slide number 2, we are going to discuss about the different units or the components which makes block ciphers more tough. So as you already know that P-box means permutation box, with the help of which whatever is the input is given, the number of bits are permutated, the position of the bits are going to be changed. But in case of Sbox or the substitution unit, whatever bits are available in the plain text, it is being replaced by another bit. So let us first discuss the P-box first. Now P-box is also called as a permutation box. Now the purpose of using the permutation box is to transpose the bits. Transpose the bit means the position of the bits are going to be changed. And in different modern block ciphers, we use 3 types of P-box. One is straight P-box, second one is compression P-box, and the third one is the expansion P-box. So let us first discuss about the straight P-box. As the illustration shows, straight P-box has the property that whatever is the number of input of the straight P-box, the same number of output is being received. Only the difference is the position of the bits are going to change. But if there are 4 bits in the input, we will receive 4 bits in the output. So, and the number of possibility by which we can do the transposition with the help of a straight P-box is factorial n, where n is the number of input. If there are 4 input, so there are 16 possibilities by which we can transpose the position of the individual bit. Suppose we have 1, 2, 3, 4. There are 16 possibilities by which 1, 2, 3, 4 can be converted into in the form of an output. Second one is the compression P-box. Now the property of the compression P-box says that number of input and the number of output is always less than the number of input. That is why it is called compression, meaning thereby 4 bit as an input, and in the form of an output you are receiving only 3 bit. So 4 bit is converted into 3 bit, or 4 bit is converted into 2 bit. that comprises the compression P box. So in this particular compression P box, we used to leave certain bits uh, of a certain position, and so that we will have the number of output less than the number of input. Of course, this compression P box is keyless, and the purpose holds the wholesome purpose is to reduce the number of bits in the form of the output. Now the third one is the expansion P box. Now the purpose of this expansion P box is to increase the number of bits in the output, meaning thereby expansion P box is a counterpart of the compression P box. In the compression P box, we are having number of bits in the input is more than the number of bits in the output. But in case of compression P box, number of input is less and the number of output is more. Of course, this also is a keyless process, and it increases the number of bits. This is an example of a uh, expansion P box. Now this expansion P box, you can see that we have 3 elements in the input, but we are receiving 4 elements in the output by assigning a particular bit of the input at two certain places. Now as far as the invertibility is concerned of the any P box is concerned, whenever we talk about the straight P box, this is invertible. Straight P box is invertible, meaning thereby since number of input and the some number of output is same, so if 1 2 3 4 is going to become 1 2 2 1 4 3, so with the help of 2 1 4 3 we are able to get the 1 2 4 3, so it is invertible. But as far as the compression P box as well as the expansion P box are concerned, these two boxes are not invertible. These are not invertible. Only straight P box, meaning thereby any permutation box is invertible if the number of inputs and the number of outputs are same. But if number of input and the output are different, then it is very difficult to find out from 4 input how to get 3, and then from 3 how to get 4. So because it is clueless, and same thing lies with the expansion P box, that in the expansion P box we have 3 inputs and 4 outputs, and with the help of 4 output it is not able to get the 3 input. So this is about the P box. Now let us discuss something about the Sbox. Sbox stands for substitution box. Now Sbox can be thought as as the picture shows, as a small substitution cipher. However, the Sbox can have a different number of inputs as well as the outputs. The input may be different, output may be different, or it may be same also. So you can say that the input of Sbox could be, suppose it is n-bit word, but the output can be m-bit word. So where n and m both may be same or both may be different. So although that Sbox it can be using key or it cannot be. It means it can be keyed or it can be keyless. And modern block cipher normally uses the keyless Sboxes. Keyless Sboxes where the mapping from the input to the output is predetermined. Now, this is an example which has been shown in front of you, that we have 3 inputs where the leftmost input is represented as the first column where 0 and 1 is written, and the rightmost input bits are 0 0 0 1. So if the input is 0 0 0, then the output will be 0. If the input is 0, if the input is, let me give you, if the input is 0 1 1, then the output will be 1 1. So it is going to reduce 3 bits. 3 bit is the input, but the output is 2 bit. Now, as far as the invertibility of the Sbox is concerned, Sbox are the substitution cipher in which the relationship between the input and the output is defined by a certain table as it is shown here. So the leftmost in this table, the leftmost bit of the input defines the row, and the rightmost two bits are defining the column. So the output is the value where the input row and the column meets. So wherever they are going to meet, that value will be the. So as far as the invertibility of Sbox is concerned, since the Sbox are the substitution cipher in which the relationship between input and output is defined by a table, so Sbox may be invertible, it may not be invertible. So in an invertible Sbox, those Sboxes which are invertible in where the input and the output is same. If the input and the output is not same, then that case Sbox cannot be invertible. But those Sboxes which gives input number certain number of bits and output bits and the input bits are same, in that case that Sboxes will be a invertible. Now the third component of modern block ciphers are the exclusive OR. Now exclusive OR is a very important component and very often used in many kinds of the algorithm, because in this process in the modern block ciphers, whatever addition or the subtraction operation is being performed by a single operation, it is performed by using the exclusive OR operation, because the all the 5 properties which an algebraic system holds, it also suits to the exclusive OR operation. The first property is the closure property. Now the closure property means that the result of any exclusive OR operation of a 2n bit word will also be an n bit word. Whenever we do XOR operation with 2n bit words, the resultant will also be an n bit word. As far as the associativity is concerned, associativity, it also holds the property of associativity, exclusive OR operation. For example, X exclusive OR within bracket Y exclusive OR Z bracket close is equal to bracket X exclusive Y exclusive OR Y bracket then exclusive OR Z. Similarly, it also holds the commutative property, that is X exclusive OR Y is equal to Y exclusive OR X. So, and as far as the identity is concerned, there is existence of identity, and whatever number of input is being used, the same 000 bits will be the identity. And as far as the inverse element is concerned, every data block is the inverse of itself using the exclusive OR operation, because it is the property of exclusive OR operation that if we are doing exclusive OR operation of X and Y and you are getting Z, if you are doing exclusive OR operation of X and Y and you are getting Z, then if you do exclusive OR operation of X and Z, you will be getting Y. So every element is inverse of itself. The next component is the complement. Now, of course, the complement is a unary operation, and in this modern block cipher, we are more interested in the complement operation in relation to the XOR operation. Suppose Y is a complement of X, then X XOR operation with Y, it is equal to Z. Then X XOR operation with Z, it will be giving you the Y value. The next component is the inverse. Now, as far as the inverse is concerned, the inverse of a component in a cipher makes sense if the component represents the unary operation. For example, unary operation, for example, keyless P box or keyless S box can be made invertible if they have the same number of input and output, as we have already discussed. And the second one is the inverse of XOR operation can make sense if one input is fixed. Now, here I am going to give you an example. Now, suppose X is the input and we are doing the encryption process with the help of key K. So we are doing XOR operation. We are doing XOR operation of X with K to get Y. Now, if we do, now in the decryption side, we have Y as the input, and if we do XOR operation with the same component K, definitely we will be getting the X, because it is the property of XOR operation. So X XOR K is equal to Y, then Y XOR K will be equal to X. Another component of modern block cipher is the circular shift. Now, circular shift, uh, as we have seen that there are many components. So, as far as the modern block ciphers are concerned, the circular shift is another component with a circular shift operation. Whenever we talk about circular shift, it is circular shift operation. And it can be either the left shift operation or it can be a right shift operation. Whenever we are doing the left shift operation and we are shifting 3 bits left, so this B5, B6, B7 will be shifted to the right side. That is why it is called circular shift. And whenever we are shifting right, we are doing right shift operation, then we are 3 bits shifting is done, then B2, B1 and B0 will be coming from the right hand side. So if there is a left shift or right shift, both are possible. So normally how now this circular shift is invertible, because if in the encryption side we are using left shifting of the operation, left shifting operation, then in the decryption side we can use the right shifting operation. Now, as far those circular shift operation is a invertible operation. The next one is swapping. Uh, you have seen in DS in the last video that we are using swapping process, and the swapping process used to happen in the modern block cipher, uh, and it is a special case of circular shift with the condition that the k is equal to n by 2, meaning thereby this operation is valid only when the value of n is even, and this is also self-invertible. What we have done, we have 8 bits, and this 8 bit is converted into two parts, B0, B1, B2, B3, and B4, B5, B6, B7. Now B4, B5, B6, B7 has taken place on the right hand side, and B0, B1, B2, B3, which was on the left side, becomes the right hand side. And that is what we are doing in the encryption side. And whenever we are doing it on the decryption side, again it is being uh, divided into two parts, and B4, B5, B6, B7 will become the left side, left side, and B3, B2, B1, B0 will become the right side. Now, the next component is split and combine. Normally, splits of n-bit word from the middle, and then combine means to concatenate two equal length words to create an n-bit word. So what we do in the split and combine, if we have n-bit word, we splits the n-bit word into two parts, and uh, on the other side, whenever we are receiving two split word, we concatenate these two words to become a full length word. So it is also invertible. Split and combine is also, split is done on the split is done on the encryption side, and combination is being done on the decryption side. Now, coming to the actual uh, topic on which I want to discuss, it is the diffusion and the confusion. Now, the Shannon has given this idea of introducing the product cipher, and it will be using the diffusion and the confusion process. What is the product cipher? It is a complex cipher combining the substitution technique as well as the transposition technique. This is already discussed in the previous lecture, that we have substitution cipher, we have transposition cipher, but we also have a product cipher. Substitution cipher is a kind of a cipher in which we are substituting a particular character by another character, and in transposition cipher we simply change the position of the character. But the particular cipher which combines both the operation, that is substitution as well as transposition, that is called the product cipher, and it has given by Shannon. Now, what is the idea of diffusion and the confusion? The idea of diffusion and the confusion is very simple. So the idea of diffusion is to hide the relationship between the ciphertext and the plain text. Now, what is the idea of that diffusion? The idea of diffusion is that if there is change in one character of the plain text, it is going to change many characters in the ciphertext. And that is why the diffusion holds the relationship between the ciphertext and the plain text. So it is going, any attacker who is sitting in between will not be able to identify, because if there is a change in the plain text, one bit is being changed, then there are many bits in the ciphertext which is going to be changed. That idea is known as diffusion. But the idea of confusion is to hide the relationship between ciphertext and the key. Meaning thereby, if there is change in key bit, one key bit is going to change many bits of the ciphertext. So that is creating a confusion. So what is actually means that diffusion hides the relationship between the ciphertext and the plain text, and confusion is going to hide the relationship between ciphertext and the keys. Now, we have seen in the DS that we are using many rounds. Then what is the idea of using the rounds? Diffusion and confusion can be achieved by using an iterated product cipher, where each iteration, we have seen that there in each iteration we are doing a combination of, we are doing applying Sbox, we are applying Pbox, we are applying other components, we are swapping, we are XORing, we are changing, and so on. Now, the diffusion and confusion can be achieved by iterating the product cipher, where each iteration will have the combination of Sbox, Pbox, as well as the other components also. And each iteration is known as round. Now, as far as the block cipher is concerned, it is using the key schedule, or you can say the key generation or key generator, that creates different keys for the different rounds. So if there is n round cipher, then it means in n round ciphers the plain text will be converted into a ciphertext n times, and for all n times we are doing all the iteration process, and for every n time we will be using different keys, and that keys are known as subkeys. Now, the block cipher uses, as I told you, that it uses a key generator that creates the different key for each round from the cipher key. So, if there are n rounds, the plain text will be encrypted n times. Now, this is an illustration which is showing the different rounds uh, which is being utilized, in which this is a basic diagram in which two rounds are being used. We have an 8-bit plain text. I have taken an example of an 8-bit plain text, and that 8-bit plain text is divided into 4 parts, each of 2-bit, 1, 2, 3, 4, 5, 6, 7, 8. And then we have a round key generator where the actual key value is k. For round number 1, we are generating a sub key, that is k1. Now this k1 key is being mixed with the 1, 2, 3, 4, 5, 6, 7, 8 bits of the plain text to get an 8-bit output, and individual 2 bits has been, they become the input of the individual Sbox. We are using 4 Sbox, and each Sbox is producing the same number of output as the input. So 2-bit in 2 input in the Sbox 1 is creating 2 output. 2-bit input in the Sbox 2 is creating 2 output, and so on. And then Pbox is being applied. And after applying P box, the individual bits which has been received from the S boxes are permutated. The bits position are going to change, and you can see the first bit of S box 1 will become the sixth bit. The second bit of S box 1 will become the first bit. The third bit will become the third bit. The fourth bit, which is the second bit of S box 2, becomes the seventh bit, and so on. So it is the working of the permutation box by which it is the bits positions are being changed. And so we will be receiving an 8-bit middle text. Now this 8-bit middle text is again in the second round. It is being mixed with another key which is generated from the same key K. But since it is round number 2, so K2 is generated, and this K1 and this K2 is different. Now this K2 is being mixed with the 1, 2, 3, 4, 5, 6, 7, 8 as the middle text, and then it is applied Sbox applied to the Sbox to get 8-bit output, and then again the P box has been applied to receive the 8-bit ciphertext. So this is how the modern block ciphers with the different component. Of course, the component which is being used is the key mixer, the Sbox, as well as the P box. Now, how we can say that there is a confusion and the diffusion which occurs in the block cipher, and for that I have taken a very simple example. And if you carefully go through this illustration, you will find out that how confusion as well as diffusion used to take place. Now, suppose we have a plain text, and this plain text has having 8 bits. 8th bit of the plain text is XORed with the K1 key, bit 8 of the K1 key, to produce a single bit. Bit 8 of plain text is combined with bit 8 of K1 to get the output, and that output is input to the Sbox. Now this Sbox, S4, is creating 2 output, that is 7 and 8. Now this 7 and 8 is the input to the permutation box, where the 7th bit will become the 4th bit and the 8th bit will become the 2nd bit. Now this 2nd bit and the 4th bit, this is the middle text. So the 2nd bit is XORed with the 2nd bit of K2, and the 4th bit is XORed with the 4th bit of K2, and this value is given to the Sbox, and this S1 is creating 2 values, 1, 2, and S2 is creating 2 values, 3 and 4. So it means, and then it is applied to the permutation box, and in permutation box the first bit is becoming the 6th bit, 2nd bit is becoming the 1st bit, 3rd bit becoming the 3rd bit, and the 4th bit is becoming the 7th bit. So let us now discuss about the diffusion. Now suppose there is change in the 8th bit of the plain text. If there is change in the 8th bit of the plain text, then the 7th and 8th bit will be changed. The 7th bit and the 8th bit will be changed. If 7th bit and the 8th bit will change, the 2nd bit and the 4th bit will change. If the 2nd bit and the 4th bit of the middle text will be changed, then the 1, 2 of S1 output and 3, 4 of S2 output will be changed. It means which is going to give the change in the 1, 3, 6 and 7. So meaning thereby, if there is a change in single bit of the plain text, that is bit number 8, you will feel changes in the bit number 1, 3, 6, 7. So single bit change is going to create changes in many bits in the ciphertext. That is confusion. Now let us now discuss about the confusion. What is the meaning of confusion? Suppose that so that is why it is said that diffusion is going to differ the relationship between the plain text and the ciphertext, because any bit of the plain text is changed, many bits of the ciphertext is going to change. So diffusion is going to hide the relationship between the plain text and the ciphertext. Now the confusion, on the other hand, confusion is going to hide the relationship between key as well as the ciphertext. So how it is possible? Now suppose there is a change in the bit number 8 of K1, and if it is so, the value of 7 and 8 will be changed. If 7 and 8 will change, the 2 and 4 will be changed. If 2 and 4 will be changed, 1, 2, 3, 4 will change. And so the 1, 3, 6, 7 will change. Meaning thereby K1 की एक bit, only one bit number 8, if it is changed, it is going to create many changes in the ciphertext. So this is going to create a confusion. So that is the meaning of confusion and diffusion, and that is why it is said that diffusion hides the relationship between plain text and the ciphertext, and confusion is going to hide the relationship between key and the ciphertext. Now, practical ciphers. Now, to improve this diffusion and the confusion, practical ciphers uses the larger data block, more Sboxes, and more rounds are being used. So, in practical purpose, just to create more diffusion and more confusion, the practical ciphers uses large data block, which is not only the 8-bit block, we are using 64-bit block. We are using not only 1 or 4 Sboxes, we are using 8 Sboxes. Instead of using 2 rounds, we will be using more rounds, that is 16 rounds, as in the case of, if you remember DES, in the DES we are instead of using 8-bit data, we were using 64-bit data. In the case of Sbox, instead of using 2 Sboxes, we are using their 8 Sboxes. And as far as the rounds are concerned, we are not using 2 rounds, but in case of DES, we are using 16 rounds. So that is just to improve the diffusion and confusion. As much as data size is being taken in the form of a block, as much as Sboxes will be used, as much as rounded will be used, rounding is being used, iteration is being used, we are going to get more improvement and able to assure ourselves that it is very difficult to obtain cipher plain text from back to the ciphertext without knowing a key. So we have 2 classes of the product cipher. Modern block ciphers uses all product ciphers with the 2 classes. The first is called as Fissile cipher, and another is called non-Fissile ciphers. Fissile ciphers are the class in which both invertible elements as well as non-invertible elements are being used. For example, DES. In the DES, we are using invertible elements as well as non-invertible elements. We are using Sbox, which is non-invertible, because we are reducing with the use of Sboxes. We are going to reduce 6-bit into 4-bit. We are using many permutation boxes. We are using swapping. We are using XOR operation in the DES. So that is why DES is an example of a Fissile cipher, because it uses invertible elements as well as non-invertible elements. Invertible elements are those elements if we are getting input with the certain process to the output. If it is invertible, then output can be used to find out in the reverse way to get the input. But non-invertible process is a process in which whatever you are getting output, you cannot get the input with that same process. And non-Fissile cipher is another one. Non-Fissile ciphers contains only invertible components, and advanced encryption standard is the algorithm which is based on non-Fissile cipher. So let us discuss first the Fissile cipher. Now, in the Fissile cipher, as I told you, that it has invertible elements, self-invertible element, as well as the non-invertible components. The Fissile cipher combines all the non-invertible. Now, if the system is using non-invertible elements, components, then by using encryption, and if we are applying decryption, how it is possible to get the proper result whenever we are applying a non-invertible. So what Fissile cipher, it combines all the non-invertible element in a particular unit and uses the same unit in the encryption as well as decryption. The process of non-inverting elements, if there are in the encryption side, the decryption side also uses the same unit. Whatever process is being adopted in the encryption side, the same process is adopted in the decryption side if there are non-invertible. And all the non-invertible elements are combined together in the form of a unit. If it is so, then encryption and decryption algorithm, how they are inverse of each other, because I have said many times that whenever we are doing encryption, converting plain text into the ciphertext, and if that encryption process involves some non-invertible element, then how it is possible to decrypt it, because it is said that decryption algorithm is the counterpart or the reverse process of the encryption. And whenever you are doing the reverse process, in the decryption, from getting the plain text from the ciphertext, then how it is possible if we have non-invertible elements. So let us discuss that also. Now, this is a simple illustration of the Fissile cipher. Now, in this P1 is the plain text. In this P1 is being mixed, XORed with the K, with the function value fk to get the C1. It means we are receiving P1 as an input, and after doing this encryption, we are getting C1 as the ciphertext. Now with this, when this C1 is the ciphertext, now how we can get from C1, how we are able to get the P1. So this is the formula which has been produced, that C1 is equal to P1 XOR with Fk by the simple illustration. If there is a P1, it is XORed with Fk to get the C1. So C1 is equal to P1 XORed with Fk. Now in this, we are doing the decryption. And in the decryption, C2 is the input. C2 is XORed with Fk to get the P2. Now if this C1 and C2 is same, then P1 and P2 should be same. Meaning thereby, if C1 which has been sent to the receiving end, and if it is C1, C2 is C1. So what is actually P2 by this decryption figure? P2 is nothing but C2 XORed with Fk. Now if this C1 and C2 is same, so C2 can be, now this C2 can be replaced by C1. If C2 is replaced by C1, because I have assumed that C1 and C2 are same. And if it is so, then C2 XORed with Fk will be equal to C1 XORed with Fk. Now we have already find out what is the value of C1. So we'll put it here. That is P1 XOR with Fk and then XORed with Fk. Now we know the property of XOR operation. If we are using the same element for the XOR operation, the resultant will be unity. That is 0, 0. So this P1 XOR Fk will become P. So meaning thereby, if C1 is equal to C2, then P2 will be equal to P. Now this mixer, whatever mixer it is, this mixer in this Fissile design is self-invertible. Self-invertible means you have to do nothing. If from P1 by applying Fk, if you are getting C1, then with C1, if you apply Fk, you will be getting the P1. That is the meaning of self-invertible. Now some improvement have been suggested on the previous design, and this improvement is given in the way that the plain text has been divided into two parts, L1 and R1. And taking R1, and then we are applying a function value, that is FR1K, where R1 is the RPT, K is the key, and this is being functioned, and then the output of this function is mixed with L1 to get the value of L2, and whatever is R1, it is R2. So So it means the input to the function is a part of the plaintext in encryption, and also it is the part of the ciphertext in the decryption. Now, when L1 and R1 is the input in the encryption side, and if we are applying FR1K on R1, and then the output of that function is mixed with L1, so that a new value of L2 is being found, and R1 is as it is copied to the R2. Now, what is happening in the decryption side? We have L3 and R3, and with the help of L3, R3, we are getting L4 and R4. Now, see, if R4 is equal to R3, because R3, whatever is the R3, it is R4. If I consider that L2 R2 is equal to L2 R3, L2 is equal to L3, and R2 is equal to R3. If we consider this, then L4 should be equal to L1, and R4 should be equal to R1. And how it is possible? Since R4 is equal to R3, and we have already assumed that R3 is equal to R2, and since R2 is already equal to R1, so we can say that R4 is equal to R1. Now let us now find out whether L4 is equal to L1 or not. So let us find out what is L4. L4 is nothing but it is XORed. L4 is nothing but L3 XORed with FR3K. So that is why it is written L3 FR3K. Now we know that this R3 is equal to R2. So it will become L2 XORed with FR2K. Now we also know that R2 is equal to R1. So this will be L, and L2 is equal to L1. Now see, L2 XORed with FR2K, because R3 is equal to R2. Now R2 is equal to R1, so it FR2K will become FR1K. And what is the value of L2? What is the value of L2? L2 is nothing but L1 XORed with FR1K. So if we replace this L2 by L1 plus XORed with FR1K, XORed with FR1K, now these two going to cancel out each other, giving the unity element. So L1 XORed with the unity element will be getting L1. So it means L4 is equal to L1. But this improvement is from the previous design, but this is also having some lacuna, that the right hand side element is copied as it is. R1 is equal to R2, R2 is equal to R3, R3 is equal to R4. So this is going to create some vulnerability. And so that is why some more improvement have been suggested. And this is the final design of the Fissile cipher. Now the improvement has a flaw. Whatever we have discussed till now, in this is having a flaw, that right half of the plain text never changes. You can see R1 is equal to R2, R2 is equal to R3, and R3 is equal to R4. So more improvement is required. So we have made some more improvement, and we are including the swapping process also, and increase the number of rounds also, introducing new elements, that is a swapper, and the effect of the swapper in the encryption is cancelled by the effect of the swapper in the decryption side. So now let us go into the detail of this design. L1 and R1 is the input. We are applying K1 to get FR1 K1. This K1 is applied on R1 with the function F, so that whatever is output, it is XORed, and the output of this will be copied into R2, and whatever was L1, it is swapped to the L2. In the next round, again K2 is being taken because it is second round. K2 is functioned with R2 with the function F, and the output is XORed with L2 to get R3, and R2 as it is copied into L3. In the decryption side, suppose we have L4 and R4. So what we do, the same process which we have done here. The first of all, what we have done, L4 is copied into R5, and whatever is R4, it is being XORed with L4K2. L4 means this L4, and this is the K2, and then it will become L5. Similarly, this L5 become R6, and R5 is XORed with FL5K1, so that we are getting the L6. Now we have to prove this, that the invertibility of this Fissile cipher design, the final design. If we consider that L3 is equal to L4 and R3 is equal to R4, if it is so, then L5 should be equal to L2 and R5 should be equal to R2. And if it is so, then R6 should be equal to R1 and L6 should be equal to L1. So let us find out whether L5 is equal to L2 or not. So what is L5? L5 is a combination of R4, see R4 plus XORed with FL4K2. Okay. Now FL4K2, L4 is equal to what? Before going to that, we have R4 plus FL4K2. So R4 is equal to R3, I have assumed it. So if it is assumed, then R4 will be equal to R3. And L4, what is L4? L4 is equal to L3. And this L3 is nothing but R2. So L4 can be replaced by FR2K2. What is FR2K2 and what is R3? R3 is nothing but it is a combination of L2 XORed with FR2K2. So it is equal to L2 plus FR2K2 and XORed with FR2K2. Now this FR2K2 XORed with FR2K2, that is cancel out each other and it will become L2. It means L5 is equal to L2. Now let us prove R5 is equal to R2. What is R5? R5 is nothing but it is L4. What is L4? L4 is equal to L3. And what is L3? It is equal to R2. So it means R4 is equal to R2. So if L3 is equal to L4 and R3 is equal to R4, we have found that L5 is equal to L2 and R5 is equal to R2. Now we have to prove that L6 is equal to L1 and R6 is equal to R2. So let us find out what is the value of L6. The value of L6 is R5 XORed with L5 and then K1. So that is what it is written, R5 XORed with FL5 K1. Now what is R5? R5 is nothing but R2. Here we have to find out. R5 is nothing but R2. So we will replace R5 by R2. We also know that L5 is equal to L2 because we have find out. So L5 is replaced by L2. So it will become R2 XORed with FL2 K1. Now what is R2? Now what is R2? R2 की value क्या है? R2 is nothing but L1 XORed with FR1 K1. So what we have done? L1 XORed with FR1 K1 and FL2 K1. L2 is equal to R1. So we can replace this L2 by R1. So it will become L1 XORed with FR1 K1 XORed with FR1 K1. So that is equal to L. So L6 becomes equal to L1. Whether R6 is becoming equal to R1 or not, R6 is equal to L5 and L5 is equal to L2. And what is L2? It is equal to R1. So R6 is also equal to R1. So this is the final design of the Fissile cipher. Besides Fissile cipher, we have non-Fissile cipher. It uses only the invertible components. And for example, Sbox need to have equal number of the input and output. In this kind of the cipher, if we were using the Sbox component, then the Sbox component is chosen in such a manner that the input and the output of the Sbox remains same. Number of bits in the input and the number of bits in the output remains same. No expansion is being done, no compression is being done. No need to divide the cipher into two halves as we used to do in the Fissile cipher. So this kind of give the idea of the non-Fissile cipher. And non-Fissile cipher is AES, that is Advanced Encryption Algorithm, is an example of a non-Fissile cipher.